Welcome to day 16 of the advent of compiler optimizations. 16 is going to be the highest power of 2 we're going to get in this series, so we should celebrate it, and we're going to celebrate it by talking about calling conventions. All throughout this series so far, I've been glossing over how parameters get in and out of functions. I've kind of explained them as we've gone, but I've kind of hand-waved a lot. We're going to look at a little bit more about what options the compiler has as we go today. And just before we start, I'm going to sort of plug something here, which I know is sort of a verboten in YouTube, but I can never remember which arguments go in which registers. And so for the longest time, I've had a little post-it note at the bottom left-hand corner of my monitor that tells me the first argument goes in this register, the second argument in this other register, and whatever, specifically for x86. It occurred to me that other people might have this problem too, and so if available on the Compiler Explorer shop is this ABI mug, and one for each of the major ABIs and architectures that are around. So there's a RISC-V one, there's an ARM one, and it's got a Compiler Explorer logo on the other side. And it has some of the simpler rules, at least, of how arguments are passed to functions. So if you want one of those, the link will be in the description. And every penny that you spend goes to support Compiler Explorer. Thank you. So with that plug out the way, let's actually look at some arguments. One of the things I'm going to do is I'm going to play around with the different types of arguments we might pass. So I'm going to set up an alias first of all here. I'm going to say using arg type equals long. Let's start with a long, shall we? And then let's write a little function that adds the two arguments it's passed together. So we're going to say arg type, or let's just say auto add arg type x, arg type y, return x plus y. So what we'll see is the LEA instruction, as we'd expect, and we're using RDI and RSI. So those are the first two arguments that are being passed in. If this was a member function, then RDI would be a hidden first parameter, which actually is the this pointer. So you'll always have to remember that when you're looking at member functions, that there is a hidden RDI at the beginning. Also worth noting is that if you're returning a big object, then sometimes the compiler behind the scenes passes the pointer to where it would like that object to be initialized. So for things like the RVO, return value optimization, and named return value optimization, there is sometimes another hidden first parameter that goes into RDI or RSI, depending on if it's a member function, and that stores the address that the calling function would like the return value to be placed into. So most of the time, RDI and RSI and RCX and RDX and all those good things are where you'll find the parameters in an obvious logical order, but just be aware that there are some other edge cases too. Anyway, we've got our LEA, we're returning rax is the return value, and we're adding the two things together. Fabulous, fantastic. What if we were to make a struct of args and say arg type x, arg type y, and then pass this. First of all, let's do it by const ref. So I'm going to say add const args am args, and then we're going to say args.x plus args.y. What we're seeing is that the first thing the compiler does is it reads the x and the y in one go using an XMM extended register from the pointer. So the pointer, this first argument, the args reference, is in fact a pointer. We've talked about this before, and we're reading the whole thing out into the XMM register. We're adding the two things together, and then we're putting the result in racks here. And these here are using parallel shifts and adds that allow it to take that XMM register and kind of add it to itself. We'll go into more vectorization stuff later in the series, but right now we can see that that's what it's doing. If we were to now pass this by value instead, so we wouldn't be reading through RDI, we'd just be passing it, what do you think happens? Let's find out. Oh, isn't that interesting? It's exactly the same as passing two longs. At least on the System 5 ABI that Linux uses, which is what I'm using here for the x86, structures that can fit into registers are passed, if they're passed by value, in those registers. And so we could actually even take two args here. So let's do args, and whoops, comma. Oh, I've pressed the wrong button on my keyboard. There we go. Sorry, I've got a funny keyboard. Oh, and now I've got caps on. args2. And what if we were to do something like args.x plus args2.x, just as an example? we see that now we're still passing these two things, these two args parameters are still being passed in registers rather than being spilled onto the stack or anything like that. That's really important, and it's an important part of the performance of a function, and something that, although you don't really want to have to think about it, sometimes it's worth knowing. So, for example, we have a number of C++ structures and small class types like span, like string view, that are designed to be passed by value. That only works well because those small structures that only have one or two elements in them can be passed efficiently in registers. So now you know that small structures can be passed in registers. That's different on the Windows ABI, where there's only 4 registers that are used to pass arguments. And I think that there was quite some discussion on the standards group about whether or not string view should be passed by value or passed as a const ref, where only one register would be used to pass the const ref, but by value it takes up 2 of the valuable slots. So important design decisions were being based off of how the ABI influences the compiler's ability to pass arguments efficiently. So let's restore our function to be just args.x plus args.y and get rid of the second parameter here. And then let's explore what would happen if we were passing things that were smaller than a whole processor register as a structure type. So I'm going to change this to be an int. So ints are only 4 bytes long. And we see that the original version still hasn't changed. We've still got RDI and RSI. The first argument is just using up only half of the bits of the register that's being passed in, the RDI register, and then the RSI register has got the second parameter in. Whereas more interestingly, in the second case, where we've got the add of the structure type, that structure type has been packed into one register. So it's being passed in just the first register, RDI. That means there's a tiny bit more work for the function to do in order to unpack it. What we can see here is it's taking a copy of the register that was passed into racks and then shifting that racks register down by 32, which brings the top 32 bits of that register down into the bottom 32 bits, and now we can add them together. So that's not quite as efficient as passing them individually, but it does have some cool implications actually. If I paste in my big example I've got in my notes, so this is a sort of extenuating circumstance version of the code here. So we're taking now, what is that, 8 arguments, and we've either got our struct type that has 8 members, or we're passing 8 independent arguments. And again, like so many of these things, please don't write code like this. I suppose the one thing going for the struct type here is that at least we can give a name to each of those arguments so that it's a little bit more obvious what they all are and you won't mix the order up when you're passing them. So don't take this as an example of how to write good code, just more as an exploration of the design space. So we can see that with 8 arguments, we actually run out of registers to pass things into. And so our original separate argument adding function here, this function has to add all of the things that were passed in registers, and then finally it has to read the 7th and the 8th argument off of the stack where they were written. So the ABI after 6 is that you put them on the stack. In the struct case, the whole thing has been spilled onto the stack as the argument is just too big to pass in registers, and so it's having to read the various chunks of the structure out, and then it does some clever tricks to add them all together at the end. But if we, for example, made this a char, now we've got 8 chars, which actually fits into one register. Over here, the separate arg version is still spilling onto the stack because the 7th and 8th parameter, even though they're only 1 byte long, have to go into the stack as we've run out of registers, discrete register to pass them in. Whereas the struct version, interestingly, is being passed in one register, RDI. So RDI contains the entirety of that structure, and the code now has to unpack them all in order to do the adds. Now, whether that's better or worse is kind of up to you, but it's just worth understanding the kinds of trade-offs that you might make when you're passing structures and arguments by value to functions, which is becoming more of a trendy way to do things, and certainly more easy to reason about than references, mutable references for certain. Anyway, that's a bit of an exploration of the space of ABI. Get your ABI mug on the Compiler Explorer store, and I hope to see you tomorrow.